Hello, and welcome back to our series on Vertex Operator Algebras. Today's installment can be thought of as an example of a representation of a Heisenberg algebra which descends from the physics of the motion of springs. More precisely, today we're going to study the simple harmonic oscillator. It is perhaps the classic problem in mathematical physics involving a second-order linear differential equation. Our dynamic variable will be the position of a mass tied to a spring, x, parametrized by time, represented by the variable parameter t. The relevant differential equation d squared x by dt squared is directly proportional to x with a negative real constant represented for convenience as minus omega squared. The solution can be represented by harmonic functions, cosine and sine of omega t. Here, of course, we assume that omega is some real number. The precise description of the physical dynamics requires fixing the constants a and b by a choice of boundary conditions. The physical interpretation for omega is related to the frequency of oscillation of a mass tied to the spring. X of t represents the position of that mass. Another physical variable of note, p of t, is the momentum, which basically amounts to the time derivative of position. Taken together, these two variables characterize the physical system, and together they can be characterized by the real, typically positive number, E, called the energy of that system. So what's so special about the energy of a harmonic oscillator? Well, it's the way that it's represented by x and p. Namely, it's a quadratic form. Demanding a positive value for the energy can be interpreted as an elliptical constraint on the relationship between x and p. It's the quintessential physics problem for a reason. Now, x and p can be rescaled by choosing a specific unit of mass, for example, so that their trajectories are circles whose radius is the square root of the energy. We can then interpret the dynamics of the system as orbits in the xp plane, the so-called phase space, as clockwise or counterclockwise motion around the relevant circle, with an angular frequency omega. With this graphical intuition, let's explore the specific details of the oscillator's motion. Suppose we pick boundary conditions such that x is proportional to cosine of omega t. That means that p of t equals minus omega sine omega t, which tells us that we can think of omega as a simple sort of angular velocity in phase space. Now, in what follows, it will be useful to complexify that phase space, and to that end, the Euler relations for cosine and sine might be useful to think about. By analogy, we'll consider complex linear combinations of position and momentum, with momentum scaled by m omega to ensure that the physicist's favorite pastime is satisfied: dimensional analysis. We'll leave the overall scaling of eta and eta bar unfixed for now. Let's rewrite our parameterization of energy in terms of these new variables, eta and eta bar. It's a little bit of work, but it's a worthwhile exercise to compute this explicitly, so please have at it. Note that we also show implicitly our desired normalization for these eta variables by pulling out the constant E. These new variables, eta and eta bar, can be thought of as directly parametrizing the clockwise and counterclockwise solutions. This is basically the same trick that 19th century mathematician Dirichlet did. This is basically the same trick that 19th century mathematician Dirichlet did when he solved the wave equation. This perspective will guide us through the construction of the quantum theory. Indeed, for the quantum case, our variables of interest are x, p, and e, position, momentum, and energy. In the quantum theory, a physical system is modeled by a special kind of vector space, and the dynamical variables like x, p, and e are a special kind of operator on that space. Unsurprisingly then, the study of quantum mechanics often amounts to the study of operator algebras, which of course is why we're here talking about this. Our defining algebraic relationship between those operators is given by the commutator of x with p. Somewhat similar to the Heisenberg algebras we've studied so far, we see that x with p is basically an imaginary constant. The associated commutator of eta with eta bar is a real constant, which you can readily show with a bit of algebra. Now, be precise and finally explicitly state our normalization for these variables, let's write out eta and eta bar in terms of these operators x and p. Note that some people would like to put carets or hats on their operators, and we'll leave them off as it should be clear from context what we're working with. Now, with this normalization, the commutator of eta and eta bar equals unity, which brings us to a familiar set of operators, 1, eta, and eta bar. It's a fun toy example of the Heisenberg algebra. Great, but these are still operators. To understand the physics, that is, the physical states of the system, we need to explore the space of states that these operators act upon. And to do that, we need to recall some details from the representation of Heisenberg algebras, which might lead you back to some of our previous discussions, say from sections 16, 17, and 24. The physical space of states is built up from those von Neumann modules. You know, those irreducible representations of a given Heisenberg algebra, M of k. Of course, following section 24, we will also fix k equal to 1, commensurate with our choice of normalization for those etas. Let's go back and look at the energy operator. The spectrum of that operator, the eigenvalues and eigenvectors, here phi sub e, essentially amounts to the set of possible physical states that can be observed directly. Reframing the energy operator in terms of eta and eta bar will help us characterize these observable states with ease. A first step in that direction is applying a little algebra. We find that the energy operator has a constant piece, energy that's always present, for free. But that's related to the ordering of the operators eta and eta bar. Indeed, this constant is analogous to the ordering ambiguity from the L0 operator from the Virasoro algebra we discussed in sections 21 through 23. Now, those eta operators, and therefore the space that we're considering, isn't exactly z-graded in a meaningful way. It's a trivial grading. But, nevertheless, we will follow our nose and turn our attention to the symmetric tensor algebra of those eta operators trying to represent this space. Okay, to quickly recap, we're interested in the space of physically observable states for the quantum harmonic oscillator, which brings us to the spectrum of the energy operator, which we are about to construct explicitly. To build the spectrum of H, we'll start with the traditional form with a constant term. From there, we'll need to compute two ingredients, the commutators of H with both eta and eta bar. Using the simple Heisenberg algebra, you can easily show that these are directly proportional to eta and eta bar themselves. Note the minus signs and the normalization, and try to verify these as an exercise for yourself. Now, taking the existence of such a spectrum for granted, we now consider states of the form eta on phi sub e for some phi sub e in the spectrum of H. As it turns out, H on eta phi sub e is also an eigenvalue of H. That is, it's also in the spectrum of H, with an eigenvalue of e minus h bar omega. You can carry this calculation through almost exactly with eta bar. Here you'd find the eigenvalue e plus h bar omega. Therefore, given any state in the spectrum, we can create another one by acting upon it with either of eta and eta bar. The eigenvalues are either raised or lowered by a quantized amount, h bar omega. This is the construction of those so-called raising and lowering or ladder operators, eta and eta bar, and it's credited to Paul Dirac. And it has direct applications to the theory of representations of Lie algebras. So this kind of terminology and these ideas will arise again and again. Now, back to the representation of the harmonic oscillator's Heisenberg algebra. On physical grounds, there must be a state with a smallest possible energy. That corresponds to the system just kind of standing there, staying still, doing basically nothing. So let's call that smallest possible energy E sub 0. Because it's the smallest possible energy, the lowering operator eta must annihilate that associated eigenstate phi sub E0. Annihilate is a technical, if silly term in physics, but it's basically a definition imposed by demanding that E sub 0 be the lowest energy state. For those of you who might be concerned that that is not a well-motivated thing to do, I hear you, and I've totally been there. you might recall that our discussion of Heisenberg module representations that satisfied the vacuum condition G sub k necessary to prove the Stone-von Neumann theorem. As in that case, it's just a technical condition on the space of physically meaningful representations. Other sorts of representations may well exist mathematically, but might not be irreducible or physically relevant. A great example of such a representation can be found through the study of so-called coherent or Glauber states. Now, given that eta annihilates our lowest energy state, or ground state, to use the physical term, we immediately see that the constant piece of our energy operator directly corresponds to this smallest possible energy. Interesting. Another way to frame what we're building here is a lowest weight representation of the Heisenberg algebra. Since we can always act on phi sub E0 by any number of eta bars to get energy levels that are increased by ever more and more factors of h bar omega, all of those states ascend from the lowest energy state. One fact that might alarm you is the existence of a non-zero energy in the ground state. This so-called ground state energy is a hallmark of traditional quantum mechanics, and has been interpreted to suggest that no system really stands still. There is some inherent uncertainty between position and momentum of a given particle, but there's a long story behind that. Okay, to make contact with what we've been studying so far, let's take our tower of states, which is trivially z-graded, and construct one with a non-trivial grading. To do that, we first need to find a non-trivially graded algebra of operators. To that end, we might simply index n many copies of eta and eta bar, say with an index alpha. We can then immediately construct the Heisenberg modules from prior discussions, as all members are effectively polynomials in the now indexed operators eta bar, acting on the ground state. You might want to check out our previous discussions from section 23 for the relevant details. Okay, so let's see if we can understand this new graded representation from a physical point of view. The operators eta and eta bar were related to a simple mass on a spring, a simple harmonic oscillator. The amplitude of that oscillator, which is related to the energy of the system, was quantized in units of h bar omega. And thus, the amplitude of oscillations effectively amounts to the number of times eta bar acts on the ground state. For the n-graded case, we have n copies of eta and eta bar, which we can interpret as being a system of springs each tied together. Note that just having a system of n identical copies of the one spring is a different kind of arrangement altogether. Although using the power of formal series from Chapter 2, we can connect these two via sort of an analytic continuation. But there is so much depth to that statement that it probably warrants its own series of lectures. When you have a bunch of springs tied together, the system tends to act like a string. And when you quantize all these operators, you end up with a quantized string. To better understand what this means, we can borrow tools from Fourier analysis and see how motion propagates on this basically infinite collection of joined springs. Hopefully now you see where that n grading is coming in. So, you might ask, what's the ground state energy of this system, this quantized string? Is it just n copies of h bar omega by 2? Wouldn't that be infinite? Well, not quite, because the collective motion of all of these springs together won't have the same angular frequency. You've got long-range Fourier modes and shorter ones. And well, frankly, I'm not going to give you any precise answer at this point, but consider this something of a motivating discussion. Let's suppose the string itself has a finite length. Then, you'll have a wavelength the size of the whole string. And of course, you'll also have one that's half that size, and then a third that size, and so on. So each oscillator has its own angular frequency. Well, for a fixed wave speed, having the wavelength doubles the frequency. So we get the ground state energy multiplied by 1, plus 2, plus 3, plus 4, and so on. Which, you might recall, takes us to minus 1 over 12. And back to the world of Dedekind eta functions and all that modular stuff we've been discussing so far. I think I better just leave it there for now. Next time, we'll review some details on SL2F before diving into Chapter 3. Thanks for watching. See you next time.